Okay, so in the beginning of chapter 5 in the first lecture, when we did Lewis structures and how to draw them and the skeletal arrangement, et cetera, what we were really referring to when we talked about electron pair geometry and molecular shape was what we call VSEPR, valence shell electron repulsion. Basically what this means is the structure of the compounds, it takes on the structure it does because of what it's bonded to, what lone pairs are present, and it determines all their properties, their polarity, their reactivity, their boiling points, their melting points, all these kinds of things. So when we talk about skeletal structures or structures, we're talking about arrangement of the atoms, we're talking about types of individual bonds, and also the overall polarity. So as an individual bond, polar, nonpolar, ionic, but then what is it overall? So bonding theory is what's going to predict the shape of molecules. This one right here. So we talked about molecular geometry, or molecular shape means the same thing, and electron pair geometry, where molecular geometry or molecular shape, when it is three-dimensional, it only describes the shape of a compound, speaking about the attachments, kind of ignoring the lone pairs on any central atom. So we're going to have characteristic, quote-unquote, corners that tells us the positions. So think of, instead of 12, 3, 6, and 9 o'clock, think more of 2, 4, 8, and 10 o'clock, okay? And we call these bond angles. How the bend goes is a bond angle. I'm not requiring you to memorize bond angles. So when we talk about these electron groups, we basically just have a central atom right here, and then the surrounding electron groups, and those can be either attachments or lone pairs. So the Lewis model, it helps us predict what things are going to look like big picture. You know, when we first start doing these, a lot of people will write water like this. But we know that because of these VSEPR theories, it's really like this. Now, electron pair geometry would take into account the lone pairs and the attachments, making this tetrahedral. But molecular shape says, we're just going to call it bent, because it clearly has this kind of shape. It's bent, okay? So 5 basic arrangements, it's just going to depend on what's happening, what's going on. So I'm going to talk about this chart, which I've uploaded for you and is printable. If you prefer the colored copy because it's just a little bit more clear, then you can go ahead and print this slide out on your color copier. But if we're looking at this and we look at what's going on, we're going to have electron groups, and then lone pairs, and then attachments, and the electron geometry and the molecular geometry. So let's just talk about this right quick. So if I'm talking about this group right here, every single one of these examples has a total of 4 groups. Now these 4 groups could appear differently. It could be 4 things that are bonded with no lone pairs on the central atom. That's going to give us what we call a tetrahedral shape for both electron pair geometry and molecular geometry. We could say there are 3 things that are bonded and only 1 pair of lone electrons. We did this example in the first lecture, NH3, and it's going to look like this. They really should have put the lone pairs there. This is going to be tetrahedral for electron pair geometry, and trigonal pyramidal for molecular geometry. Tetrahedral because it counts all 1, 2, 3, 4 things. Trigonal pyramidal because we can see that kind of triangle base and the lone pair gives it that peak. So trigonal pyramidal. We could have two attachments and two sets of lone pairs, like water. That's also going to be tetrahedral, because there's four things, for electron pair geometry, but bent for molecular geometry or molecular shape, because there are these lone pairs which are counted in electron pair geometry, but they are not counted in molecular shape. If I go down here, for example, all the examples here have 6 total electron groups or electron densities or electron clouds. They all mean the same thing. So again, electron pair geometry is going to take into account those electrons, where molecular shape only deals with the attachments. So if I have 6 groups or 6 bonded and no lone pairs, for electron geometry, it's going to be octahedral, and same for molecular shape. They're both going to be octahedral. Once I get into lone pairs and attachments, this is where these shapes and how we identify them differ. So I could have 5 attachments and 1 lone pair. 1, 2, 3, 4, 5. Here's my lone pair. And you can see that this exceeds the octet rule, because bromine has 2, 4, 6, 8, 10, 12 electrons on the central atom. So that's going to be an expanded octet. It will be octahedral for electron pair geometry, and square pyramidal for the molecular shape. So where does that square pyramidal come from? Well, here's those lone pairs that we're going to ignore with molecular shape. Here's your square, and they all kind of make a pyramid with that one extra attachment. Okay, that's where that square pyramidal is coming from. Now, 4 attachments, 2 lone pairs. 1, 2, 3, 4. Here are my lone pairs. All of these for electron pair geometry are going to be octahedral. For molecular shape, because we ignore the lone pairs, it's just square planar. It's square, and it's flat like the Oklahoma plains, right? Kind of like trigonal pyramidal and trigonal planar, where there either was or wasn't lone pairs. So in this case, there's an attachment making that pyramid, so square. Here, there's no attachment because it's a lone pair instead, so just square planar. So I recommend going through these conceptual connections. Again, the answers, I believe, are in the end of the chapter after the example problems at the end of the chapter, not in the back of the book. So again, just to kind of review on this, draw the Lewis structure, determine your number of electron groups around the central atom, figure out how many valence electrons are available to you, get it sorted out, figure out what's, if we need to have multiple bonds. When it comes to counting the attachments, it doesn't matter if it's a double or triple bond. What matters is that there's only one thing attached, whether it's a single, double, or triple bond. You don't have to count the multiple bonds. So if we look here, predicting the geometry of bond angles here, again, you don't have to know bond angles. I'm going to focus on shape. So what we have are 1, 2, 3, 4 groups, okay? If we go back here, here's my groups of 4. In that particular example, we had 3 attachments and 1 set of lone pairs. Okay, so 1, 2, 3, and then the lone pair. So what that tells us is that for electron pair geometry, it will be tetrahedral because it does count that lone pair of electrons. But for molecular shape, we're trigonal pyramidal. That's a terrible pyramid, but you get the idea. It's trigonal pyramidal, okay? This is going to be something that is polar because of that lone pair of electrons. I do recommend going through the rest of those examples that are in the original PowerPoints just to make sure, you really can draw it and figure out with that chart what shape it's going to be depending on if there are attachments and or lone pairs. So it's really hard to write three-dimensional things on a two-dimensional piece of paper. So in order to accommodate that, we use a straight line, dashed, and solid wedges. So the straight lines are meant to be in plane, like literally, X and Y coordinates. Where the dashes and wedges, this is meant to represent or be on that Z plane. You remember we talked about that a couple of chapters ago, where one part is kind of going into the computer screen at you, or into your computer screen, and one is kind of coming out at you. The dashed is the one that's going back or into the computer screen. The wedge, the solid wedge, is the one that's coming out at you. Okay, it's coming towards you. So generically speaking, this is just kind of how we write things with lines. That assumes everything is in plane, which is true for trigonal planar because there are no lone pairs. But if we compare that to trigonal pyramidal, remember, there'll be a lone pair here. So one's going to be in plane, one's going to be coming out at you, and one's going to be going back into your computer screen. Again, if I'm going to say this 100,000 times, if you have not got a molecular model kit at this point, just do it. Because when you build these molecules, it'll make much more sense and be much more clear. And it'll be super helpful for organic chemistry. And I believe most of you, if you're a biology major, you will have to go on to Organic 1 and 2. And the molecular model kit is a lifesaver. Don't wait, because it's going to help you with this stuff also. Amazon, less than 20 bucks. Okay, so when we have things that have multiple central atoms, you're going to see a lot of this in organic chemistry. Not so much in Gen Chem 1 and 2 sometimes, but if this were my just generic two-dimensional Lewis structure, I'm going to see a couple of things about it. I got 1, 2, 3, 4 interior atoms, meaning 4 central atoms, okay? And each one of them, depending on what they're bonded to, is going to have a different molecular shape. So for example, if I just focus on this right here, okay, that nitrogen is right here. Here's its lone pairs. It's bonded to 1 hydrogen, 2 hydrogens, and something else. Don't care what the something else is. It's just bonded to something else. Okay? So what that means is that there's 3 attachments, 1 lone pair, and that is in the category for electron pair geometry of tetrahedral, but for molecular shape, trigonal pyramidal. All right. If I look at, let me erase and clean this up. Okay, if I look at this carbon, here it is right here. There's no lone pairs, and it's bonded to 1, 2, 3 different things. 3 attachments, 0 lone pairs. It is trigonal planar for both molecular shape and electron pair geometry. When you see something like this, I'm going to tell you, do go through this example. When you see something like this, this is what you're going to see a lot of style in organic chemistry. What this tells you, the fact that it's in order the way it is, tells you that this carbon is directly bonded to those 3 hydrogens, and also directly bonded to the oxygen, and this hydrogen is bonded to that oxygen. That's what that means. So here's your carbon with 1, 2, 3, 4 attachments. So it is going to be tetrahedral for electron pair geometry and molecular shape. And if I look at this oxygen, it's bonded to 1, 2 things, and it has 2 sets of lone pairs. So 2 lone pairs and 2 attachments for electron pair geometry means tetrahedral. For molecular shape, like water, it'll be bent. When we talked about these shapes, we talked about polarity and dipole moments, and we said there was partial positives and partial negatives on different, parts of the compound. But polar bonds must have an electronegativity difference, dipole moments, and be unsymmetrical for it to be polar. Okay? You don't need to worry about vector addition. We're not going to talk about that. Polarity will affect intermolecular forces, which we don't talk about until chapter 11. So intermolecular forces are the forces that attract one molecule to, a molecule of the same thing. So like why water molecules are attracted to each other. They're not bonded to each other, they are attracted to each other. We're going to see London dispersion, dipole-dipole, hydrogen bonding, and ionic bonding. Okay? It affects boiling points and solubilities. Like dissolves like rule. What that means is something that is polar can dissolve polar things. Something that is non-polar can dissolve non-polar things. Those things are miscible. Okay? If it's non-polar with a polar, they are immiscible. They will not dissolve. Okay? So when you have your oil and vinegar salad dressing that you got to shake up every single time you want to use it, that's because the oil and the vinegar have separated out. They're not going to blend together, right? So that what that should tell you is that one is polar and one is non-polar. The oil is the one that's non-polar and the vinegar is the one that's polar. Same with oil and water. We all know oil and water doesn't mix, right? Water is our most common polar solvent. Solvent meaning it does the dissolving of something else. And it's very, very polar, very polar. So if water's polar and it doesn't mix with oil, that should tell you that oil is non-polar. This is it for chapter 5. Chapter 6 will be going up shortly.